Salutations, young warriors, and welcome to Ronin Academy. I am your sensei Hanbei. In honor of the upcoming new year, I have decided to make a final video of 2017 that will review some of the most impactful scientific discoveries of this year. And of course, what better way to do so than to describe the projects that received one of the highest accolades in the field of science, the Nobel Prize. Therefore, in the inaugural video of the SciVanguard series, I will present a layman's summary of the Nobel Prize-winning research in physics, chemistry, and medicine. First up, physics. On September 14th of 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, also known as LIGO, uncovered evidence of gravitational waves from the collision of two black holes approximately 1.3 billion light-years away. This monumental discovery provided significant empirical evidence to Einstein's theory of general relativity, and it was this importance that allowed three core scientists to receive the 2017 Nobel Physics Prize. So, what are gravitational waves and why are they important? Now, gravitational waves are derived from Albert Einstein's theory of general relativity. Therefore, in order to better explain the phenomenon, it is best to look at the theory. In 1689, Sir Isaac Newton described gravity as an invisible force that attracts two bodies of mass inversely proportional to the distance between and directly proportional to their respective masses. Now, both of these masses follow an absolute model of space shown in his tome, The Principia Mathematica. Absolute space, in its own nature, without relation to anything external, remains always similar and immovable. Relative space is some movable dimension or measure of the absolute spaces, which our senses determine by its position to bodies, and which is commonly taken for immovable space, such as the dimension of a subterraneous, an aerial, or celestial space, determined by its position in respect of the Earth. The result of this was a static view of space in which there is no dynamism, i.e., gravitational disturbances would happen instantaneously. On the other hand, general relativity is a gravitational theory posed by Albert Einstein, which correlates the force of gravity to the bending of space-time. Goemon, could you provide an example as to the superiority of GR over Newtonian space-time?
Of course. Here we see a scenario in which the Earth is orbiting the Sun.
Thank you. According to Newton, if the sun were to instantly disappear, the Earth would instantly follow a tangential path as the gravitational force is broken. However, according to Einstein, nothing can travel faster than the speed of light. Therefore, the gravitational impact of the sun's disappearance can only travel as fast as the speed of light, in the form of gravitational waves. The consequence of this idea was that the force of gravity was nothing other than objects following curves in the space-time continuum. From this example, we can see the impact of gravitational waves. Therefore, when LIGO uncovered evidence of gravitational waves released in 2016, the entire scientific community went abuzz. The three physicists who actually received the award, Rainer Weiss, Barry C. Barish, and Kip S. Thorne, were the ones who developed the techniques used in the LIGO apparatus. In summary, LIGO is actually two equivalent detectors, one in Hanford, Washington, and the other in Livingston, Louisiana. LIGO is the world's largest laser interferometer. An interferometer is a device that combines two or more sources of light in order to study its interference pattern. In the case of LIGO, a laser is separated by a beam splitter. These separate beams are then reflected by mirrors at the end of the two arms of the device. Finally, the beams are then redirected through the beam splitter to form the resultant beam. If the beams of light are out of sync by their recombination, the detector will see patterns of constructive and destructive interference, marked by light flickering. As gravitational waves alter the nature of space-time itself, LIGO's task is to attribute the actual warping of the space-time fabric to detected interference caused by changes in the length of the arms by values as small as 1/10,000th the size of a proton, making it one of the most sensitive scientific instruments in existence. Brings us to the next subject, medicine. In 2017, the Nobel Prize in Physiology or Medicine was given to Jeffrey C. Hall, Michael Rosbash, and Michael W. Young for their work on discovering the molecular mechanisms controlling the circadian rhythm. So, what are those molecular mechanisms and how do they relate to the circadian rhythm? According to the National Institute of General Medical Sciences, circadian rhythms are physical, mental, and behavioral changes that follow a daily cycle. An example of this would be the sleep cycle, as diurnal creatures like humans and sparrows follow a daily cycle of being active in the day and sleeping during the night. This is, of course, reversed for nocturnal animals. In essence, circadian rhythms are a part of a bodily system that instructs organisms on appropriate times for different physiological processes, like sleeping, eating, or hormone levels. This is why the circadian rhythm is the primary reason for jet lag. When traveling over many time zones, your destination will inevitably be offset from your internal circadian rhythm. This difference is what creates the fatigue as one tries to adapt to the new patterns of light and temperature. Even without direct observation, organisms still operate on their circadian rhythm to pace physiological processes. In the 18th century, Jean-Jacques d'Arthuis de Méran, an astronomer, discovered that mimosa plants, regardless of the presence of sunlight, still followed their circadian rhythm of opening and closing their leaves daily. In 1984, Jeffrey C. Hall, Michael Rosbash, and Michael W. Young were able to isolate the gene responsible for circadian rhythms and uncover how it operated via the PER protein. Goemon, do you mind?
No, here you go.
Thank you. Encoded in the mRNA of fruit flies, the researchers found what they later called the period gene. The gene synthesizes a protein known as PER, which facilitates the circadian rhythm by oscillating over a 24-hour period. During the day, the PER levels accumulated, while at night they degraded. From there, Hall and Rosbash created an inhibitory feedback loop that would allow the PER protein to limit its synthesis in cells. However, Young postulated that another circadian gene known as timeless, with the TIM protein, would bind to PER to enter the nucleus and inhibit period gene activity. In addition, Young hypothesized that another gene, double time, with DBT protein, would delay PER accumulation, allowing its 24-hour oscillation. In summary, these discoveries have broken the field of chronobiology wide open. Brings us to chemistry. Last but not least, in 2017, the Nobel Chemistry Prize was awarded to Jacques Dubochet, Joachim Frank, and Richard Henderson for their work on cryo-electron microscopy, which advanced biomolecular imaging techniques. In the 20th century, there were two main techniques to view biomolecules: X-ray crystallography and nuclear magnetic resonance. X-ray crystallography allowed scientists to view well-organized protein crystals via the diffraction of X-rays. The image is formed when a crystallographer compiles the angles and intensities of the diffracted rays to create a three-dimensional figure of the protein based on electron density. X-ray crystallography is unfortunately limited to only well-organized crystals. Nuclear magnetic resonance spectroscopy, or NMR, uses the eponymous phenomena of atomic nuclei in a magnetic field being able to absorb and reemit electromagnetic radiation. When placed in a magnetic field, atomic nuclei, like carbon-13, absorb EM radiation at specific frequencies indicative of the isotope. Knowing the strength of the magnetic field, then, scientists can use the measured resonant frequency to determine the isotope present. NMR's primary limitation is that it is only used optimally with relatively small proteins. In addition, both techniques only form still images that do not show any protein dynamics. In order to study bacteriorhodopsin, a protein embedded in the membrane of a photosynthesizing organism, Henderson turned to electron microscopes to avoid the limitations of NMR and X-ray crystallography. Electron microscopes work very similar to standard light-based microscopes, except that since electron wavelengths are shorter than light, the image would have finer resolution. Unfortunately, electron microscopy's use of electron beams meant that biomolecules would either be incinerated or the image quality would reduce if the beam was weakened. In addition, electron microscopy required that the molecules be in a vacuum. That would deteriorate biomolecules due to dehydration. To combat the limitations of electron microscopy, Henderson and the other prize winners developed several techniques to enhance its effect. The first was to use the entire membrane and cover the sample with glucose. By using the entire membrane, the protein maintained its form, and by covering the sample with glucose, the protein would not be dehydrated. In addition, a weaker beam was used to prevent incineration. However, using the mathematical principles of diffraction used in X-ray crystallography, Henderson was able to reconstruct a three-dimensional image of bacteria rhodopsin as each molecule would diffract the beam in the same direction. The next was to cool the samples with liquid nitrogen to further protect the sample from the electron beam, hence the name Cryo-electron microscopy. Joachim Frank created an image analysis process for randomly oriented proteins. As seen here, the electron beam would hit the proteins, leaving a trace. Then, a computer would sort the protein traces based on similarity, and then compile a high-resolution two-dimensional image for each protein. Finally, the computer would extrapolate a three-dimensional structure from the 2D images. Jacques Dubochet furthered the cryo aspect of cryo-electron microscopy through his vitrification method. Since a glucose covering does not assist water-soluble molecules, Dubochet decided to create a new method seen here. First, he applied the sample to a mesh so that it would then create a thin film over the holes. Then, the mesh would be placed into negative 190 degrees Celsius, also negative 310 degrees Fahrenheit, ethane, allowing the water to vitrify. This simply means that via the cooling, the water became a glass. The glass would then act as a new coating for use under the electron microscope. Using series of images of the same protein, scientists can now use Henderson, Frank, and Dubochet's cryo-electron microscopy to create films of protein dynamics at atomic detail, breaking the field open for new studies into atomic and molecular biochemistry. I hope you enjoyed this review of the scientific highlights of 2017 as we progress into the new year. Happy New Year's, and I'll see you again in 2018. Please look for my upcoming Zettabytes video on literary heroism. I leave you once again on your Musha Shugyo or Warrior's Pilgrimage. I hope my words were able to assist you on your critical path. If so, please subscribe and press the like/bell button below. Arigato gozaimashita, and I will see you on your way.